In this statistics video, we will be discussing the basic concepts about probability. Um, for us, we're not going to be covering odds, but some classes do cover odds. So if you are in that kind of class, please feel free to look up some more information about odds. All right, here are the basics of our probability. So number one, anytime we talk about an event is just anything that we're collecting results about or collecting information about. A simple event is an outcome that cannot be broken down into simpler components. Like if you're talking about playing cards, something like drawing, having a flush in your hand is very different than talking about just having a heart. So a flush can be broken down into its basic components, so its basic events. So that's what we mean by simple. So simple would be drawing one heart. A compound event would be drawing a flush, 5 cards of the same suit. The sample space is just all of the possibilities that could happen in your experiment, and that will depend on what your experiment is and what you're doing. So let me show you some examples. All right, first, so our procedures, we're going to be looking at a single birth. An example of an event could be just you're having a girl, and notice the sample space over here, boy or girl, right? When you have a child, it's either a boy or a girl. If you're having 3 births, like if you have 3 children, then there are lots of different possibilities. Like we could look at just the possibility that you have 2 boys and 1 girl. And there are different ways that could happen. So each of those different ways that could happen depending on age, right? Did you have the 2 boys first and then the girl? Did you have the boy and then a girl and then a boy? Those would all be simple events. So this would actually be a compound event, the fact that I have 2 boys and 1 girl, because I didn't specify the order. And then here's your sample space of all the ways that you could have 3 kids. So I think that kind of really helps you kind of narrow down what you're looking at. So when you're looking at simple events, it means you can't break it down any further. So when you have a child, it's either a boy or girl. This is a simple event. Okay, the genetics dictates this. When you have 3 births, though, you have 3 kids. The result of 2 girls followed by a boy is a simple event. Okay, so we're very, very specific about the order. Okay, we can't break that down anymore. You have a girl, and then a boy. Pretty straightforward. Like if you're rolling a die, the outcome of a 5 is a simple event. But if I roll an even, well, that could be a 2, a 4, or a 6. So that's not simple. We can break it down. So that's what they mean by simple event. So not simple event would just be saying I have 2 girls and a boy, because you're not telling me the order. Okay. Yeah, and not simple event would be, rolling an even number, again, because you're not telling me which even number. It could be a 2, a 4, or a 6. And the sample spaces, that last column, that's really important that we learn to write down all the possibilities that could happen. And there's lots of ways we could do that. A lot of people do trees. So like if for this 3 births, you could start with a tree. So like your first birth, you could have a boy or you could have a girl, and then you could go to the next birth, right? If you had a boy first, it doesn't matter. You could have a boy or a girl next. If you had a girl first, it doesn't matter. You could have a boy or a girl next. And just kind of create that tree like that. So a lot of people do that as well. Trees will help you. And then at the end, you'll have, so like this one would just be 2 children. So you could have a boy and then a boy. You could have a boy and then a girl, right? You'd have a girl and then a boy. You could have a girl and then a girl. So that will list, when you go down the tree and those branches, you can list out all the possibilities of ways that could happen. A lot of people just write them down. Notice this one, they did all the ones where you had a boy first, and then they did all the ones where you had a girl first. And then they just went in order, like all boys, 2 boys and a girl, and then just kind of moved them around. But I like doing trees. I think they help me stay a little bit more focused and more organized. There are 3 common approaches when you're finding a probability. First of all, let's talk about some notations. So before we ever start talking about the 3 different ways. Capital P denotes that we're trying to find the probability. A, B, and C you use to denote which event. So if you were to write the probability P parenthesis A parenthesis, that denotes the probability that event A is occurring. If you put a B in there, it'd be the probability that event B is occurring. So it's just a shorthand way, so you don't have to write all those words. Probabilities always lie between 0 and 1. 0 means it never happens, and 1 means it is certain. It's going to happen. The closer you are to 1, the more likely it is to happen. The closer you are to 0, the more unlikely it is to happen. So just so you know, every probability will be between these two. And if some people do them as percentages between 0% and 100%, but we usually write probabilities as a decimal between 0 and 1. All right, so let's talk about the 3 different ways that we can find a probability. The first is called the relative frequency approximation. This is where you conduct, an experiment or procedure, and then you just count the number of times that the event that you are looking for happened. So the probability of A would just be the number of times it happened versus the number of times over the number of times that you did that procedure. Pretty straightforward, right? Some people call this experimental probability. Depends on the book that you use. The second is called the classical approach to probability. This is important to note that this requires that every outcome is equally likely. So like if you have a loaded die, the sides aren't equally likely to show up. So that you can't use this approach in that. But this is only for procedures where every event is equally likely of occurring. So you just take the number of ways that A could occur and then divide that by the number of simple events that are possible. But again, be cautious. You can only use this approach when all the outcomes are equally likely. And the third way is called subjective probability. This is where we don't actually know exactly what the probability is, but we do have some knowledge of the past. So like if you're talking about the probability of a plane crashing, I have no idea. And I think that would be practically impossible to calculate just because of how many variables there are when you're flying a plane. But we do have past experience. So we can look at the past data and use that to come up with a probability. All right, simulations. Simulations are just an experiment or a procedure where the process behaves the same way, and we make sure that the same results are produced or similar results. And this is the number one problem that most studies have today, is that when anyone tries to replicate them, they can't get similar results. And it's really important that if you want to have good data and you want to make sure that your study is solid, it has to be reproducible. So simulations are really important. Other people should be able to do the same thing you did and come up with similar results. And a lot of probabilities can be found doing a simulation as well. So if somebody says this happened, I can do the same experiment. I can use the probabilities and then find out if their data was solid or not. When you are rounding your probabilities, it's always important that you use exact numbers. So if you have an exact fraction, if you change that into a decimal and it goes on forever, I wouldn't use the decimal. I would always use a fraction. But if you do have to use a decimal, please use 3 significant digits in probability. Some people use 4, but definitely 3. I try to stick with fractions. If there is a fraction, if it is exact, I'm going to use it. I'd rather use an exact answer than an estimated answer. There's something in probability called the law of large numbers. When a procedure is repeated over and over and over and over, the relative frequency probability tends to approach the actual probability. So if I do an experiment 100 times, 1,000 times, 10,000 times, 100,000 times, the more I do it, the closer I'm going to get to what the actual probability is. So you really want to make sure that to make sure that you don't confuse the fact that this doesn't apply to one outcome. It applies to all of these. So you can't use a generalization. You can just say, okay, using the law of large numbers, I know that the probability of a plane crashing is blah, which means it's very small. It's going to be, but that doesn't mean that the plane I'm about to get on might not crash. You know what I mean? So you got to make sure that you're not trying to apply the behavior of the whole to the behavior of the one. And if we know nothing about the likelihood of these different possible outcomes, you should not assume that they are all equally likely, like the plane crashing. It is not equally likely that every single time you step on a plane, it has the same probability of crashing. That is totally not true. So make sure that you're taking in all of this. Again, you really should be thinking critically about what's happening in your particular procedure. All right, so speaking of that, let's find the probabilities. Find the probability that a commercial airline will crash on any given flight. Now, this, again, we have to take that third approach because we don't know. I mean, there's too many variables that could happen. But we can go back and we can look at data. So we're going to use that third approach. We're going to go back and look at data. So So the probability that the plane will crash is equal to. Now, in a recent year, there were about 39 million commercial airline flights and 16 of them crashed. So 16 out of the 39 million flights. Okay, that's an extremely, extremely small number, right? And if I put that in my calculator, I actually did. I have 1, 2, 3, 4, 5, 6. So that's going to be 0.123456410. And so that's the probability. Again, if you want a percentage, you would just multiply that by 100. So you have a 0.1234410. So that is your percent chance of crashing based on the data from that recent year. Notice it's an extremely small number. And this is very subjective. Like that could change from year to year. Some years there might be a few because of they had the issue with the 737 MAX. So again, all this changes because we don't have any exact data. So just know that most of the time we're using actual data from the past to talk about our probabilities. All right, here's another example. In a Pew Research Center study, randomly selected adults were asked if they had seen or had been in the presence of a ghost. Okay, so 366 of the respondents said yes, 1,637 of the respondents said no. Based on these results, find the probability that a randomly selected adult says that they have seen or been in the presence of a ghost. All right, so first thing we have to do is find the total number, right? They told us the yeses and they told us the nos, but they didn't tell us the total. So first thing I have to do is add it up to find out how many people they talked to in the first place. All right, add those together and that gives you 2003. Okay, so the probability that the randomly selected adult says they have seen or been in the presence of a ghost is 366 out of 2003. And of course you would simplify that, and if it asked you to do this as a decimal, you would just divide those, and it would be 0.183. All right, so what does this mean? And this is the hard part for a lot of people, is interpreting this answer. Okay, this says that there is a 0.183 probability, or if you want to use percentages, 18.3%, right? This is the same thing as 18.3%, right? That a randomly selected adult says that they have seen or been in the presence of a ghost. It doesn't mean that 18.3% of all people believe it. It just means that I have an 18.3% probability that if I randomly select someone, they will say that they have seen or been in the presence of a ghost. And I know that there's a very fine difference between those, but it's really important that you understand what you're saying when you say this. You're not saying 18.3% of people believe in ghosts. That's not what you're saying. So again, make sure that you're paying specific attention to that. Something that you're going to deal with a lot in probabilities are called complementary events. The complement of an event A is denoted by an A with a bar over it. And this is what the outcomes in which A doesn't occur. And the cool thing about complements is that you can find them from the probability of a random event. So it's lovely. I will show you some different ways to do that. So let's go back to that. So it's back to Pew. They did another survey of 2002 randomly selected adults. 1,782 of those said that they use the internet. Find the probability that a randomly selected adult does not use the internet. There are two ways to do this. So A is that they use the internet. And our complement is that they don't use the internet. All right, so you need to find the complement, right? We need this. This is what we're looking for. So there's 2,002 people. 1,782 of them said that they do. So if I subtract that, that will be the complement. Notice, because when I add these together, this plus this is A, this is A bar, right? So that's the thing about probability. So if I want to find the probability of A bar, it's going to be 220 over 2002, which that turns out to be 0.110 approximately. Okay, another way you can do this is that you can do the probability find the probability that people use the internet and then do 100 minus the probability of A bar. So that's another thing you can do. Or if you want to find the probability of A bar, you can just do 1 minus the probability of A. That's another. So there's lots of different ways that you can use that complement to help you. But again, remember the result just means that we found the probability that the randomly selected person doesn't use the internet is 11%-ish, right? This is approximately 11%. It doesn't mean that 11% of people don't use the internet. It means that if I randomly choose someone, I have an 11% chance of choosing someone who does not use the internet. And I know that's really a very simple thing, but you got to make sure that you understand that difference. All right. Genetics is another great place that you can see probabilities used. So every parent has a type of genotype for blonde hair or brown hair. So let's just say these two parents, not all parents, but these two parents. You have these alleles that decide what your hair color is. So assume that if the child has at least one blonde allele, that color will dominate and the child's hair will be blonde. So list the different outcomes. Okay, so first of all, our parents, we've got a blonde and we've got a brown, and each of them have this, right? So we could get the blonde and the blonde from each parent. So that's the first thing that could happen. We could get the blonde, blonde. So blonde, brown. Oh, whoops. I should probably write that a little bit nicer. Okay, let's try this again. Blonde, brown. All right, so if each parent has this, so this is the first parent, this is the second parent. They both have that. Okay, we could get the blonde from this parent plus the blonde from this one. So you could start with blonde, blonde. Okay, what else could happen? You get blonde from the first parent, you could get brown from the second parent. So you could end up with blonde, brown. Okay, then you could end up with the brown from the first parent, but blonde from the second. So you could end up with brown, blonde. Or you can end up with brown from both of the parents. All right, so there is your possible outcomes. There's your total sample, everything that could possibly happen. Okay, now it says, what is the probability that a child of these parents will have the brown-brown genotype? So notice we have 4 things in our sample set, and only one of them has brown-brown. So 1 out of the 4. And that is 25, right? 0.25, 25%. What is the probability that the child will have blonde hair? Remember, it said if they have blonde at all, then they're going to be blonde. So that one has a blonde, that one has a blonde, and that one both has blonde. So 3 out of the 4. So that's 75%. So being able to establish your sample set of events, that's very important so that you can then break it down. And you will see use of genetics. Sometimes they use Punnett squares to do these. There's lots of different ways to do this. They can use those trees again. So again, it's just what you feel more comfortable with. Some people can just do the list. I'm perfectly comfortable doing whichever method you want to use. All right, when you are identifying significant results in probability, there are some rules. How do I know if something is significant or not? Because obviously there's going to be a lot of stuff around the middle, and then there's the people on the outside, the outskirts, the really high or the really low, and that's what we're looking at. We're looking for, so under any given assumption, the probability that a particular observed event is very small, and the observed event occurs slightly less than or significantly greater than what is typically expected. All right, we can conclude that the assumption is probably not correct. So the question becomes, then how do I tell? And we're going to spend a lot of time later on talking about how can I measure that? How do I know when something is significantly high or significantly low? All right, so for now, when you're talking about probabilities, the significantly high number of successes is when there is a probability of 5% or less that would happen. So say, you're talking about like your child, right? It's about it's a pretty much 50-50 chance, right? You either get XX chromosomes or XY chromosomes. There's very few variations on that. There are some abnormalities, but it's usually 50-50. So if I go to the hospital and I say, hey, from the last 100 births, how many were females and how many were males? And they tell me, oh, we had 80 girls and 20 boys. It's like, whoa, like that. What is the probability that that's going to happen? And if that probability is less than 5%, then we consider it, hey, that's significant. And that 5% is not absolutely rigid. It could be 10%. Some people go as low as 1%. You want that probability to be as small as possible because that shows that your data is solid. You don't want to have a 25% probability that your results were not high or low. So that's something we have to think about. Same thing goes if they're significantly low, right? If I'm looking for girls and they go to the hospital and they say, oh, we had 85 boys and 15 girls, right? Wow, that's pretty low. So again, 5%, this is not rigid. It'll change depending on what's going on. More about this and ways to measure it so that we actually have some numbers to put with it in later lessons. All right, so just to wrap things up, remember that the probability of an event is either you can write it as a fraction, so it's exact, or a decimal to 3 significant digits between 0 and 1. Right? Remember, 0 is an impossible event. 1 is an event that is absolutely certain to occur. Notice the notation for the event and then the notation for if the event does not occur, the complement. So make sure you have all that notation down because we're going to use it a lot in further lessons. So we'll see you next time.